Okay, welcome everyone to the JAC colloquium. It's a pleasure to have Michele Fumagalli today. I've known Michele for almost 20 years now when we were students in Milano Bicocca. He studied in Milano and then he did his PhD at the University of California, Santa Cruz, working with Xavier Prochaska. Then he got the Carnegie Princeton Fellowship and stayed for an extra year in California. And then in 2014, he moved to Durham, first as a reader, then lecturer, professor. And then in 2020, he finally moved back to Italy, where he's now a professor in the university where he studied. And and he's currently working there. So Michele has been a very prolific scientist, working in very many different aspects of galaxy evolution, and in particular on how gas gets in and out from galaxies. And we're eager to learn what you're working.
Well, thank you very much, Roberto. Thank you, everyone, for joining me today and for giving me the opportunity to share with you some of the work we have been doing in the past few years to characterize the gas environments of galaxies. I'm sure, let's see if this was, yeah. I don't have to probably give a lot of introduction for why we care about the environment where galaxies live. But the main idea is if you want to understand the evolution of galaxies, we can collect a lot of information by looking at the light that comes from the galaxies. But we can also complete this picture by broadening our view to what is around the galaxies themselves. This is an image that reproduces the starlight of galaxies out of a simulation. So it's an artificial image. And if we look at the gas that is around these galaxies, this is what we see. So we see this network of gaseous filaments, and the galaxies sit within them. And so the processes that are key to drive the evolution of galaxies occur along these filaments. So the gas is flowing towards the galaxies to feed star formation. As you know, following the formation of new stars and then the evolution of the main sequence, one star goes supernovae, and energy is injected back, and this energy pushes material back into the intergalactic medium through galactic outflow. And so if you want to understand this exchange of gas, which we call the baryon cycle, we want to focus our attention on the gas envelope near galaxies. So the region that is known as the yellow gas, or more recently as the circumgalactic medium. So this is this special buffer between the interstellar medium, where things happen inside the galaxy, and the large-scale structure, and the intergalactic medium on large-scale structure. And so this is where we're going to put most of our emphasis in order to understand how this gas exchange is instrumental for the evolution of galaxies. So the technique to study this medium has varied with time, as I'll show you, but classically, this problem has been approached in terms of combining absorption spectroscopy with spectroscopy in emission. The idea is that most of the gas we see around galaxies is quite tenuous, has densities that are typically much below 1 particle per centimeter cube, and so it's quite hard to see in emission. And so the idea is to go in the region of the universe where we have bright sources like quasars, which we can use as background probes for the gas we want to study. And so if you are interested in understanding what's happening around the galaxy, you basically collect spectroscopy of the background quasars that are unrelated. They don't have anything to do with the systems you're studying, but you use them as background lights, and you look for the shadows, basically, of the gas in absorption. And then, of course, you need to also collect extensive information of emission spectroscopy of the galaxies themselves to know, first of all, where they are. So you need quite extensive coverage of the field in terms of density. And then with this spectra, you can also learn about the physical property of the galaxies and try to put together the two. This is an approach that has been taken routinely in the past 10, 15 years, and especially using multi-object spectrograph, people have characterized the gas environment of galaxies across many redshifts. And here I'm just showing you an example of what we know of Lyman break galaxies. So these are fairly massive and highly star-forming galaxies we see around redshift 2 and 3. And what you see on the left-hand side is a plot that shows the column density of neutral hydrogen, so how much gas we see near the galaxies in projection as a function of distance from the galaxy. And what you see, so 0 is where the galaxy sits. Basically, 0 is very close to the galaxy, and then big numbers of the x-axis are moving away from the galaxy. And you see that there is a decrease in profile. So basically, this tells us that galaxies sit in over densities of neutral hydrogen. On the right-hand side, you see a similar measurement done in a slightly different way, where the color you see in the map tells you what is the optical depth of the gas you probe in absorption. So it's again a metric of how much gas is there, where red is there is a lot of stuff that absorbs, and blue is not so much. And now this is shown along two coordinates, so the x and y axis. So the x-axis is the transverse direction. Again, you have a galaxy you want to study, and the transverse direction is how far you are from that galaxy in the plane of the sky. That's the x-axis. And the y-axis is in the Apple flow. So you basically measure the difference in redshift between the galaxy you're studying and the gas you see in absorption. And again, you see that in the bottom left corner, which is close to the galaxy, you have the highest amount of material. And this is now done not only for hydrogen, but is also done for heavy elements. And so not only star-forming galaxies live in regions of overdensity of neutral hydrogen, but they are also surrounded by enriched material. And by looking at the shape of these colors, you can, through models, you can also learn about the contribution of inflows and outflows in the signal we're measuring. So this is all very nice, very interesting. It has been somewhat hard to do because with multi-object spectrograph, you can get many galaxies at the same time. But if you really want to have a complete view of the galaxy population in the field, you have to go back over and over and over, so it gets quite expensive. Also, you have to target galaxies. So you have to do imaging, identify the galaxies you're interested in, and go and follow them up. And so the approach you really want to take to go forward is one in which you go blindly to the field and you try to collect as much information for as many galaxies as possible in a more efficient way. And this is where integral field spectrograph, like MUSE at a very large telescope, have really changed the way we approach this problem. Here I'm showing just an example of a field that is imaged with MUSE. This is a special field. I'll go back to this, but there are two quasars in this field that are marked with circles, and these are the sources you can use to probe the gas in absorption. On the right-hand side, there are just small stretches of the spectra to just show you an example of the type of data we can gather. Now, MUSE is an integral field spectrograph, which means that for every pixel of that image, you also get a spectrum. And so without any pre-selection, you can go in your cube and basically get redshift for as many galaxies as you can, up to a certain flux limit. But you can also look for a signature in the spectrum of emission lines of galaxies that don't really show up in the continuum. And so it's an instrument that is very, very sensitive for studying line emitters that are undetected or hard to detect in continuum. And so if we do this exercise by looking, for instance, at Lyman alpha, this is what we see. And so you see that over this field that covers a bit more than 1.5 arc-minute square, we detect several hundreds of galaxies, and then you can basically correlate the position of the galaxies quite easily with respect to where you see the gas in absorption. And so this is really transforming the way we approach this study, as I said, for two reasons. One, we can go to fainter galaxies, and so we're really pushing down in terms of mass. We're not limited to Lyman Bray galaxies at high redshift, but we can go and reach, for instance, Lyman alpha emitters at much lower stellar mass or halo mass. And then we reach an unprecedented completeness, because basically up to a certain flux limit, everything that is in the field is detected. The other thing that comes out nicely of this type of cubes is volume. And so you don't have to really tune your observation to a certain redshift, but you basically get almost the entire visible range, and then let you access several emission lines across different redshifts. So this is a plot that at the bottom shows the typical absorption line you get in quasar spectra when you observe in the optical, and on the y-axis you see the typical transitions you can detect, and on the top you see how integral field spectrograph like MUSE, also when complemented with a near-infrared spectrograph like the Wildfield Camera 3 on HST, or similar instruments now offered on JWST, let you basically probe a big redshift range through optical or UV emission line. And so we are really, with this technique, we can now really study faint galaxies across a big stretch of the cosmic history. And so in Milan, we have been focusing on three large programs that we have led on Hubble Space Telescope and on VLT, using MUSE to basically apply this technique and characterize the baryon cycle, so the connection between galaxies and the gas we see in absorption across a significant part of the cosmic star formation history, which is highlighted here with these three bands. So the programs I'll tell you about today are mainly the first two. So the MUSE survey, which is a MUSE survey that targets about 30 quasar fields with moderate depth observations. So these are typically 5-hour MUSE observation on each quasar. And then we have a program which we call the MEBF, so the MUSE Ultra Deep Field, where we go very pointed onto this special field that has two closely separated quasars, and we integrate for over 150 hours just pointing at that region. So we go extremely deep in that particular region. You can find many results from these programs in the literature, and today I would like to highlight three key results for you. So the first one is to share with you what we have learned about the gas environment of low mass galaxies that now for the first time we can access and study with this technique. So that's the first part of my talk. In the second part, I'll show you clear evidence that there is a connection between the galaxy environment, so how many galaxies are in your surrounding, and the property of the CGM. So the property of the CGM are affected by the galaxy environment around. And then I'll show you also how we've been able to go past this idea of combining absorption line with galaxies in emission by looking directly at the circumgalactic medium and also the intergalactic medium directly in emission, again, using MUSE. At any time, feel free to interrupt. If there is something you'd like to ask, I'll be happy to take questions as I go. Okay, so the first part, what we have learned about the gas environment of low mass galaxies. So, as I said, these are LEs, so Lyman alpha emitting galaxies, which we see around redshift 3, 3.5, because that's where Lyman alpha enters the MUSE wavelength range. And compared to Lyman Bray galaxies, they are roughly a factor of 10 lower in terms of stellar mass or halo mass. And so we're really going an order of magnitude deeper into the galaxy luminosity function. And using especially the MUSE survey, we've been able to now assemble very, very large samples, orders of magnitude bigger than what was previously possible. And so we have samples of more than 1,000 such galaxies that we can correlate with several hundred absorption lines. And so we can, for the first time, approach this problem also from a statistical point of view, which is again another novelty that has been brought by MUSE. And this cartoon here shows you the key result, and then I'll explain how we get there. But to just get you started and oriented, so this is what we learned. We learned that these Lyman alpha emitters live in gas filaments that connect multiple galaxies. And these gas filaments contain most of the neutral hydrogen we see in absorption. So for aficionados of the field, these are the Lyman limit systems. They are systems that are optically thick when looked with the quasar, so column density of the order of 10 to the 17 and above. And so we have these filaments that contain partially neutral hydrogen connecting many galaxies, and there are also heavy elements inside these filaments. And this is what is shown in the cartoon with this gray and red scale. But we also have evidence of pockets of gas that are more diffuse, so they don't contain a lot of neutral hydrogen, but they do contain weak presence, so diffuse presence of metals. And we attribute this to previous episodes of star formation. So basically are relics of episodes of star formation that appear as these sort of like bubbles surrounding these Lyman alpha emitters. So this is what we infer. Now I'll show you some data that support this idea. And so the first thing you want to ask yourself is, okay, now I have two data sets. I have my quasars, out of which I measure absorption lines. So I know where the absorption lines are in redshift space. And I have a galaxy population. Are the two things connected at all? And so what you can study, for instance, is the distribution of galaxies in volumes that are centered on the absorbers. And this is what we have done on the left-hand side, where we compile the luminosity function of Lyman alpha emitters when we sit on strong hydrogen absorbers, and this is the green line, when we sit on metal systems like carbon-4 and silicon-4, and these are the black and the pink line. If you compare this with a random region in the universe, which is shown in red, you definitely see that once you are selecting a region of the universe where you see optically thick gas or metal-enriched gas, you tend to find many more Lyman alpha emitters than average. Okay, we are much more elevated, not quite at the level that we see around quasars, and this is shown by the blue line. And so basically, there is an excess of galaxies close to regions where we see strong absorption in the quasar. On the right-hand side is the same thing, just expressed in a different way, is the projected two-point correlation function, so the excess probability of finding a pair of an absorber in a galaxy as a function of not angular, but linear separation. And again, you see that for carbon-4 and what we call APS, which is hydrogen absorber, there is a positive clustering signal. And so the two populations are not just randomly there, distributed at random, and so there is some overlap, but they are genuinely associated, so they know about each other. Yet another way of seeing this, which adds more information, is studying the number of detections across systems. On the left-hand side, again, we select regions with hydrogen absorption, and we count how many LEs we expect. In gray is what you would expect at random. So most of the time in this volume, we would expect to find nothing, so no galaxies. But we do find 2/3 of the time at least one galaxy. And an element that will become relevant later is that we have quite a significant fraction of cases where we find actually multiple galaxies near the same absorbers. When you look at metals, the picture becomes a bit more complicated or interesting. It depends on the point of view. And so on the right-hand side is again the same thing. It's like you sit now in a region where we see carbon 4 in absorption, and we ask how many galaxies there are. But now you see multiple colors for each bin. So at 0, you see there are 4 color bars. So these are split by the strength of the absorption, where purple is a weak line and yellow is a strong line. And then there is the in-between. Okay? And what you can clearly see is that if you sit on a strong carbon 4 absorber, so you have to look at the yellow bar, there is clearly an excess of galaxies that are detected associated with this absorber. While if you look if you sit where weak absorbers are, so that's the purple bars, you see that most of the time you don't see anything. Okay, so that seems to be a much more stronger association between the stronger carbon 4 absorber and the galaxies than the weaker. Okay. And so there seems to be a difference basically in the behavior with which galaxies are associated according to the strength of this metal content. Okay. Okay, so this is in terms of statistical association. Now, can we look a little bit more into the distribution of galaxies with respect to the gas in terms of like space? And so what you can do is basically remember the setup is the following. We have a quasar, and so we measure a redshift, a gas cloud. So the only easy information we can access is how far the galaxies are with respect to the sight line. Okay, and that is what describes the impact parameter. Okay, it's basically the projected separation between the galaxies we see and the gas we see in absorption. On the left-hand side is the distribution for H1, and on the right-hand side is for carbon 4. And you see that there is a wide distribution, but the bulk of the galaxies are found at distances that are certainly above 50 kiloparsec and more towards 150 to 200 kiloparsec from the gas. Okay. These are, as I said, low mass galaxies. A low mass is order of few times 10 to the 11 or so. And so the virial radii for these laminar emitters are small, typically the order of like 20 kiloparsec or so at this redshift. And so we are clearly seeing gas that is associated with these galaxies, but is definitely not at very close distances. It's not the distances that are below the virial radius. Okay? So we are basically not probing the inner circumgalactic medium, the inner halo gas of this galaxy. We are seeing gas that is physically associated, but on scales that are much larger than the typical halo, dark matter halo of these galaxies. Okay. Yeah, please.
The question is not normalized by, right?
No, this is just frequency.
So it's okay to have more larger scale because
it's okay, but the experiment
no, I understand.
By chance, yes. So this is not just a trivial R square. Because they are not random. So suppose the universe was such that all the hydrogen was coming from the CGM of these LEs. With this experiment, the distribution would have been much more like this. Okay, and so the fact that there is an association that shows, for instance, for the projected phosphorescence function, and the fact that the distribution is like this is that the gas is in some system that is physically associated, but not in the inner CGM. And so where is it now? That's the next part. So if you want to try to gain a little bit more insight about the spatial distribution, you can perform an experiment like the one we did. And so this is an image of one of the field where at the center you see the quasar. And the quasar is basically pinpointing the position where we see the gas in absorption. So that's where the gas cloud we're probing is. And in blue here, you see the various galaxies we detect at the same redshift as the gas clouds. Okay. Now, for systems where we have multiple detection, you can basically identify a galaxy. Doesn't matter which one. You can take the brightest, you can take the closest. Doesn't really matter. And you identify basically a line that goes from one galaxy you select to the gas cloud. Okay. And now you ask, where are all the other galaxies with respect to this direction? Okay. If it was a random distribution, there was no reason to prefer certain angles. So you would expect to find basically galaxies isotropically distributed. If there is some preferential morphology to the gas structure that we are probing, you would see something different. So we went ahead and measured this. On the left-hand side is when we measure it for hydrogen. In blue is for a random sample. Again, so it's like you shuffle redshift, and so basically this is a control sample. If there is no physical reason for the connection, what you see is isotropic distribution. So basically there is no preferred angle with respect to that line where you find the leads. When you look at the data, there is an excess for small angle of 480 degrees, which basically means that once you draw this line between an LE and the gas, all the other LEs that are associated with the system seems to be either very close to the line or on the other side. And basically, this is suggesting that we are looking at something that is not isotropic, but is more along some sort of filament. Okay. For the carbon hole, things are slightly more complicated because remember I showed you that there seems to be a different behavior if you look at the strong absorbers compared to the weak ones. And so the analysis now is done in a slightly different way, but similar concept. Try to understand whether systems tend to be preferentially co-aligned or isotropically distributed. And so if you focus on the purple line, the solid one for now, this is telling you the fraction of times that you find multiple galaxies aligned for systems that are stronger than what's shown on the x-axis. Okay, so moving to the right on the x-axis gives you progressively stronger and stronger absorbers. And higher numbers means that most frequently, the galaxies associated with the strong absorber are aligned along this filamentary structure. The dashed line is the complement of that. Okay, and so if you now look for the weakest absorber, and so you now use the x-axis no more as a lower limit, but as an upper limit. So it's like what's happening to the galaxies that are associated with the systems that are weaker than what's shown on the x-axis. Now you have to read the number on the yellow lines. Okay, so for the weak systems, you see that the fraction of align and not align is basically 50%, which means they are isotropically distributed. There is no preferred direction. And so out of this, we basically gather that the gas we see in absorption for the H1 and for the stronger metals is associated with the galaxies, but is not coming from the CGM of these individual galaxies. It's more coming from some filamentary structure that connects multiple galaxies. Conversely, we have evidence of a weaker association between these low column density or low equivalent weight carbon core absorbers. And in that case, the distribution of galaxies with respect to this gas seems to be more isotropic.
Sorry, Michele.
Please.
So the first purple point basically includes all galaxies, all meters, because it includes all galaxies above that.
It's cumulative, yes. But it's done. So this is done selecting the absorbers, and then you count the fraction of LEs for the subset of absorbers that has.
Okay.
So thinking in another way, this includes all absorbers, and then going to the right, we only subselect the stronger one. So and out of those, what fraction of detected galaxies lies at small angle or isotope?
So it's okay that the first purple point is not the same as the last orange one.
The first. And that's a bit of a piece of mind, but yes, it's not, because for the orange, now the equality goes in the other direction. For the orange point.
So they are basically including different gaps.
There is, of course, overlap. Okay. Okay. I'll skip this, but if people are interested, then I'll explain. But basically, this is showing, okay, it's like what you show me, I believe it or not, up to you, but it's done for a subsample. Okay, so you show you that in a subsample of fields, the optic gas you see there is associated, we propose, with this filamentary structure. Now, the question is this typical of all the optic gas we see in the universe? Or is it just typical of a subset of such system? And basically, we have done statistical analysis to show that if you take the typical extent we are probing near these LEs, and you scale that by the typical number density, so number of galaxies per co-moving volume of these LEs, you find that what we're seeing here is typical of the entire population of optically absorbers. So said in a different way, now you go to a random survey of quasars, and every time you see optically thick gas in absorption, statistically, basically, what we've shown you applies to that system. So the configuration we have shown you in this system holds for the entire population of optically thick absorbers. Okay, so the proposal we have is that the bulk of the optically thick absorber we see in quasar survey arises from these filaments that connect these multiple LEs. And it is, of course, not just LEs, because inside the structure you can have Lyman-Break galaxies, you can have quasars. And so our proposal is that they are not distinct populations, but we're just tracing the same large-scale structure inside of which there are multiple galaxies. LEs tend to just be the more abundant tracer compared to Lyman-Break galaxies or quasars. And so this is why we have a better sampling, basically, of this structure when we go to LEs. Okay, so this basically hopefully convinces you of this picture again, once again. So we think we are basically using Lyman alpha emitters as tracers of these gas filaments that contain the majority, if not all the optically thick gas we see in the universe at H3. Strong metals are distributed along the same filaments, while there is a looser association between the galaxies and the weak metal absorbers. And in that case, we also see more isotropic distribution. So this is what justifies this idea of these basically clouds that are metals that are there, but they don't seem to be directly connected with the population of star-forming galaxies we see now. So this is where the idea of these relic bubbles comes in. Okay, so that's part one. There are pressing questions on this, please.
A question, but the overabundance of Lyman alpha emitters around absorbers, right?
See?
But isn't it at least partially implied by the fact that we are looking at the absorbers? So if there are absorbers, it's because there is an emitters behind.
Well, I guess it depends on the knowledge or prior knowledge you want to attribute to this. Following from our result, I would say yes, but think of this as a sort of like experiment. Like now you know only about the gas, and you don't know about the galaxy population. So you go and look, and you find that there is an excess. Okay? Suppose there was in an extreme universe a complete anti-correlation between optically thick H1 and LEs, then you wouldn't see this excess. So maybe it comes to you as natural, but this is the first time it has been measured at this mass scale. So maybe I'm not understanding the question.
Sorry, can I ask another thing?
Please.
So when you show the comparison between the H1 and carbon-4,
yes,
I think if I understand correctly, you're presenting that as, we're looking at the hydrogen gas and the metals, but carbon-4 is highly ionized.
That's right. Yeah.
So how do I need to think about that? Like, where does the energy come from? And is that a substantially different type of gas that we are studying compared to H1, not just because
yeah, no, that's a very good question. I skipped this a bit, but so you're absolutely right. We are probing different gas phases. We're a bit limited in terms of the tracers we can use. I'll show you later on. We have efforts that are going back to these fields in the infrared to get Mg2, which is more similar in ionization than hydrogen. So there is some complication to the ionization. We have checked explicitly that the following is true. So for the very strong carbon-4 absorbers, there is, in the same spectra, there is a good fraction, or like 50%, of association between the H1 and the strong carbon-4. And if you select the strong carbon-4 and you stack on the H1, you do see that there is a more prominent absorption than if you select the weak absorber and you stack the H1. And so basically, it's not really addressing the ionization problem, but is a proxy to say that there is a physical association at the absorption level between the strong carbon-4 absorber and this H1. Of course, that gas is intrinsically multi-phase, and so I'm not claiming that the same atom necessarily gives you H1 and the carbon-4, but this is suggesting that the same structure harbors both the H1 and the strong carbon-4. While when we look at the weak absorbers, we don't see such a strong correspondence. And then I'll take your point that is more complex if you really want to go to a physical model for what sets the ionization. Most likely is a contribution of three things: the spectrum, the UVB spectrum, in close proximity to galaxies definitely have an excess, so a local radiation field, and a fraction of the carbon-4 can actually be collision ionized. And so there will be a phase that arises from a warmer gas phase. Okay. Part one. Part two. Let's bring in now the correspondence between or the impact that the galaxy environment has on the CGM. From the point of view of galaxy evolution, we understand very well, it has been studied for like 20, 30 years now, that the fate of a galaxy is really determined by the environment in which the galaxy lives. We know that if galaxies are in overdense environment, with time, they tend to become more passive. If they are in less crowded regions, they tend to preserve, with time, the ability to form stars. I argued that the CGM is this special region where this baryon cycle happens, and that baryon cycle has the influence basically the fate of the galaxy. And so it's probably obvious to most of us to think that as the environment influences the activity of galaxy, then the environment needs to also affect the property of the CGM. Okay, so there needs to be some effect on the galaxy environment on the CGM. So this is a very plausible hypothesis, one which though was very, very hard to probe before the advent of MUSE. And this is because it goes back to what I was showing you. So relying on multi-object spectrograph, it was very hard, especially at high redshift, to characterize in detail the galaxy overdensity around the absorber. In previous studies, you were kind of lucky already if you were finding a galaxy that was also associated with an absorber. So let alone characterize the galaxy environment around the galaxies that you're associating with the absorbers. Now with MUSE, we get this complete picture. Okay, complete always to a flux level, of course, but we can very easily characterize the galaxy environment near the absorber. And so for the first time, we can explicitly measure whether there is a visible impact of the galaxy environment on the CGM. Incidentally, MUSE has also enabled fun studies at lower redshift, redshift 0. And this is just such an example to also give you a cartoon view. So this is a system we studied with MUSE of like 3 galaxies that are interacting. And this group is coherently unfolding inside a cluster. And what you're looking at is the map of the H alpha. And you see basically that the interactions in the form mostly of tidal interaction are displacing gas from the ISM away from the galaxies inside what we would call the circumgalactic medium, the yellow gas. So this is basically a picture that really shows you the process of gas removal from the ISM into the circumgalactic medium of group gas. So now we can clearly see it in emission with MUSE. Going towards higher redshift, already by redshift 0.5, doing such studies in emission is complicated. And so we need to resort again on absorption line studies. And around redshift 0.5 up to redshift 1.5, we can select Mg2 absorption. This is again gas that is kind of cool and enriched and is close to galaxies, to the yellow galaxies. And what we have done is to basically study whether there is a difference in this distribution when we consider galaxies that are mostly isolated, here shown in red, or galaxies that reside in group. What is shown on the y-axis is the covering factor. So it's the fraction of the area around the galaxy that is covered by gas or by Mg2 at a certain equivalent width limit. And the x-axis is how far you are from the gas. Okay? You basically see that there is a clear excess of covering factor for group galaxies. So group galaxies tend to have more Mg2 gas or more extended, so a bigger cross-section of Mg2 gas compared to isolated galaxies. On the right-hand side is the strength of this Mg2 absorption as a function of the galaxy over density. There is a bit scatter, but there is clear indication that at the highest over densities, you have the strongest Mg2 absorbers. You may wonder, well, that's obvious, because now you have, instead of one single galaxy, you have multiple galaxies. And so my sight line goes through more stuff because there are more halos. This is what is called a superposition model. And so basically nothing is really happening to the CGM. It's just in projection within a group. You just see more stuff because you probe more halos that are close to each other. In this plot, we have studied this effect where we construct a model for the superposition, which is done with this empty circle in gray, and the real data for groups are in blue. And of course, there has to be some superposition. So some of the signal comes from superposition, but you probably noticed that the blue stars, the real data, are on average higher compared to the superposition model. And so we think there is some physical excess that comes from a physical alteration, basically, of CGM properties of group galaxies that pushes gas in a different configuration that we see in absorption. We can also replicate this study at much higher redshift. So going back to our LEs, a redshift 3.5, and we have done this now with different tracers, neutral hydrogen, ionized carbon, and as I was saying before, we now have a new program where we go back and also probe the full Mg2 gas. And again, we split the covering factor, so the cross-section of absorbing gas as a function of distance from the galaxy by isolated galaxies and group galaxies. Even at high redshift, you see the same signal, clear excess of gas in the CGM or the structure surrounding these LEs. Now, the exact physical processes that are operating here are at the moment unclear. This is as much as we can pull out of the current data. And so we need to start resorting to modeling here. The two hypotheses we have is that towards the lower redshift, we see probably something similar to what we see in the local universe, where we have interactions within groups where material is displaced. At high redshift, I was arguing that we're not really seeing the inner CGM of the galaxy, but we are seeing more of this larger scale structure. And so the origin of that signal, that accessing group, might be different. And it might be due to how basically these filaments are distributed inside the regions of the universe that are overdense. But this needs to be verified more with models. Last thing, if I have a couple of minutes more. Okay. Just want to show you very quickly how we can go beyond what has been done so far in absorption. Now, by trying to understand to what extent we can learn about the CGM gas or intergalactic medium by probing this tenuous gas directly in emission. So this was almost impossible before the advent of integral field spectrograph. But now with MUSE, we have much higher sensitivity to low surface brightness line emission for a very obvious technical reason that we can discuss later if you want. And so we have done this experiment now in terms of detecting gas in emission in a few environments. So we started a few years back looking inside SSA22, which is a rich protocluster, redshift 3.1. What you're looking here is the image of all the galaxies we see, background, foreground, everything is projected for SSA22. This is the continuum. If you now select the emission line and the redshift of this protocluster, you basically start seeing this Lyman alpha emission, which is diffuse, and it has a morphology that starts hinting basically at some filamentary structures that are traced by Lyman alpha. You can study more in detail the galaxy population inside this SSA22 structure with respect to the diffuse gas in emission. On the right-hand side is the slice of the MUSE cube at the redshift of the structure, where we have space and space on the two axes, and this is velocity, okay? And the galaxy population, especially some millimeter galaxies, AGN and X-ray AGN, is marked by this symbol here. And you basically see that there is a quite strong correspondence between the galaxy population and the filaments, both spatially and in redshift space. So basically, Lyman alpha is starting to trace explicitly this large-scale structure, this filamentary structure that connect these very active galaxies at redshift 3. More recently, we have exploited the ultra-deep observation in the MEVF, which I explained is this field where we have two quasars that sit at a separation of about 500 kiloparsec in projection. These quasars are physically at the same redshift, and by looking at Lyman alpha, we now see clear evidence basically of a filament that connects the two quasars. This is a region where we have two quasars that are very close by physically and in projection, and now with very deep MUSE observations, we can basically trace through Lyman alpha the filamentary structure that connects the two quasars. Given the quite high signal to noise for this very low surface brightness signal, we can also start studying not just the detection of this gas, but learn about the distribution and the physical, the morphology of this gas. And what we can do is surface brightness profiles in the direction of the filaments, where the two lines are whether you sit on one quasar or on the other. Okay, and so the point here this is actually the midpoint in the filament. And what comes out very nicely of this analysis that you see a change in the slope of the profile. And basically, we have a direct measurement of the transition between the circumgalactic medium and the intergalactic medium. So going back to the picture, by measuring the surface brightness profile going in this direction, we see a change in the surface brightness profile, which happens to be around the virial radius for the halos that are hosting the quasars. And so it's a direct measurement, one of the few, if not probably the only direct measurement, the transition between the CGM and the IGM in emission at this redshift. We can also measure the surface brightness profile across the filament. And so basically now you sit on the filament and you cut in this direction. And so you basically look at the surface brightness profile going away from the filament in the transverse direction. And this is what we find here. Okay. Also measure that with quite high signal to noise. And then I'll leave you with just a last example of detecting now the metal-enriched CGM from normal star-forming galaxies. And so now by stacking many galaxies, we've been able to detect Mg2 in emission and O2 in emission from normal star-forming galaxies. And we have been able to also study how that signal varies as a function of, for instance, stellar mass. This is shown for Mg2 here at the top. And you see that the emission gets more extended as you go towards high stellar masses, but you also see a hole in the center because you actually start seeing the line in absorption against the continuum of the galaxy. I'm running out of time, so I don't go through details, but if you're interested, we can talk about it. Then you can actually start comparing with models and you can learn about whether your favorite simulations. We have done a comparison with TNG in this case, reproduces or not the signal. And unsurprisingly, we find that for robust comparison, you really need to have detailed energy transfer calculation on the top of the simulation. Otherwise, it's very hard to compare the shape of these profiles. I close, thanking you for your attention. Just with a thought toward the future, where do we want to go next? There are two directions. Well, in the future, ELT will give us the ability to probe even lower halo masses, and so really push to the dwarf regime. So dwarf galaxies are unexplored, especially at cosmic noon, but they are just the most abundant population. And so most of the metals that are around there have to come from the dwarf galaxies. And so it's exciting to think that by extending this type of study to even lower masses than we can probe now, we can actually try to understand the origin of the bulk of the metals within the universe at those redshift. And then we have big cosmological surveys ongoing, Euclid, JPass, EDEX, that are giving us redshift of galaxies as a function of redshift over large areas of the sky. And there are also absorption-like surveys with DESI, soon foremost, soon WEAVE, that give us data quality that now is science grade, at least for statistical analysis of the correspondence between absorption line and galaxies. And so we will be able to extend this type of studies, not to just thousands of galaxies, but to millions of galaxies across a large area in the sky. And this is where you'll basically start having constraining power to really tell apart different models for the baryon cycles. And then I'll, again, thank you for your attention. And I'll leave you with this last summary slide. Thank you.